Welcome to the 24th lecture on computational mathematics with Sage Math. In this lecture, we will look at first some calculus on polar coordinates, and then we will start multivariable calculus. We shall look at how to find limit of functions of 2 variables and 3 variables, and then we should also look at what is meaning of continuity and all these things, etc. So, let us get started. So, first suppose you are given a function in polar coordinate, let us say r is equal to f theta. So, for example, here f theta is 2 minus cos 2 theta and theta varies between 0 to 2 pi. So, we have seen how to plot graph of such functions. So, how does one plot graph? So, you need to use polar underscore plot, and when you run this polar underscore plot of r, and theta varies between 0 to 2 pi and fig size is 4. So, this is what you get, this is the graph of the function. Okay. Next, suppose you have another function, let us say 1 plus 2 into cos 2 theta, again theta varies between 0 to 2 pi. So, its graph looks like this. This is somewhat more complicated, right? So, and if you for example change theta range, so for example if I say theta varies between 0 to pi itself, you will get only half of the graph, right? So, let us say we will make it again 2 pi. So, that is the graph of 1 plus 2 cos 2 theta. Okay. Next, let us look at how to plot tangent to a curve 1 plus 2 cos 2 theta at theta equal to pi by 3. So, what we can do? So, we have r is equal to f theta, and where we know that in polar coordinate we have x is equal to r cos theta and y is equal to r sin theta. So, in Cartesian coordinate, if you substitute x equal to r cos theta, y equal to r sin theta, this function will get converted into polar coordinates. Now, what you can do is you can find derivative of x with respect to theta, derivative of y with respect to theta. I have denoted it here by x theta, y theta, and then you can take the derivative of y with respect to x, that is dy d theta, and then you can ask it to show this. You can ask it to show. So, that is the derivative of this function r is equal to f theta at theta, and you can find out the value of this derivative, that is the slope of the chord at theta equal to pi by 3. Let us okay, so make it pi by 3, here also pi by, so everywhere I will make it pi by 3. Yeah, and then what are we doing? So, pi by 3 is somewhere here. So, that is not it is at the origin. So, let us make it at pi by 4, pi by 4 everywhere. So, we are plotting the slope at theta equal to pi by 4 and the point at this point. So, this is the point at pi by 4. So, let me change this problem, instead of theta equal to pi by 3, let me make it pi by 4. So, here is the graph of this curve along with the point. Now, at this point you can draw the tangent, and so for that you need to define the equation of the tangent, which is in slope intercept form. You have the equation of the tangent whose slope is m, and it passes through x1 y1. Here x1 y1 are the x coordinate and y coordinate of this point. So, that is the tangent, and let me plot the curve along with the tangent, and this is what you get. So, that is the tangent at this point. So, that is fairly simple. Similarly, suppose you want to find area of a curve in polar coordinate. So, area of a curve defined in polar coordinate is given by integral of half r squared d theta, theta varying between a and b. And this formula is quite simple to obtain. One can use change of variable and obtain this formula from the Cartesian coordinate, or you can look at what is the small area element in polar form. That will be, suppose if you draw small area element here, and theta varies, this angle is d theta, then and suppose this is the r, then r, this area will be half into base into height. Height you can consider as r, and base will be for small area element, small arc, this height will be actually r sin theta, but sin theta for theta small is very close to theta. Therefore, you will get area element as half r square and d theta. So, you integrate this, you will get the area, right. So, let us look at, suppose we want to find the area of this polar curve r is equal to 2 plus 2 cos theta, theta going from 0 to 2 pi. This is what is called lemma cone, and so in this case this is the graph, and its area is given by integral of half r squared with respect to theta varying between 0 to 2 pi. So, that is the 6 pi. This 6 pi is the area enclosed by this particular polar curve. Similarly, suppose you want to find the area of the region inside this circle 4 sin theta and outside this cardioid r is equal to 2 sin theta minus 1. So, how do we find out? So, let me define the two curves as r1 and r2, and those curves, let us plot those curves. So, when we plot these two polar curves, the blue one is the circle which is 4 sin theta, and the red one is the cardioid which is 2 sin theta minus 1, and we want to find area inside the circle outside this cardioid. So, this is the portion whose area we want to find out. So, let us plot this in shading. So, first we need to find out what are the point of intersection of these two curves, so that we can use solve command. So, solve r1 is equal to r2 for theta. So, you will see that the theta is in this case minus 1 by 6 pi, but we want this theta to lie between 0 to 2 pi. So, this will be actually 1 will be 2 pi minus theta, that is 2 pi minus theta, which is pi by 6, and other one will be here. So, this, let us write that at first one as pi plus pi by 6, and the second one is 2 pi minus pi by 6. So, these pi theta 1 is going to be 7 pi by 6, and theta 2 will be actually 11 pi by 6. So, these are the, and now let us plot the area inside this by using the option called fill and give the fill color. So, that is the portion whose area we want to find out. This is the in orange color. Now, let us find out the area. So, if you want to find the area under this curve, so this is r1, this is r2. In this case, r1 is bigger than r2. So, we can find area as half into integral of r1 square minus r2 square, and theta varies between theta 1 and theta 2. So, when you compute this area is 5 by 3 into pi minus 1 by 2 square root 3. Okay. So, this is how you can find area under polar curve. Similarly, you can find arc length. Again, arc length, if you look at in the Cartesian coordinate, you can use change of variable formula and obtained arc length formula in polar coordinate like this. So, let us look at one example. Suppose we look at the circle. So, circle can be written in polar coordinate as r is equal to constant 1, circle of radius 1. So, if I want to find length of this circle, this already we know it should be 2 pi. So, let us compute this and see the answer is 2 pi. So, this formula is correct, and let us look at, suppose we want to find the length of the arc r is equal to cos square theta by 3 and theta varies between 0 to 6 pi. So, let us first plot graph of this polar curve, and this is how the graph looks like. And when you find the length of this curve, so this in this case you can what you can do is, suppose we plot this function, this curve between this and let us say 6 pi by 4. So, this is the only 1/4, and the length will be 4 times this. So, that is what we are doing. We will look at the length between 0 to 3 pi by 2, which is 6 pi divided by 4, and multiply this by 4, and when you compute the integral, you can look at the numerical value of this. It is 10.7704, right. So, this is how you can find area length of polar curve, and similarly you can also define what is the surface of revolution of a curve defined by polar coordinates, and try to find out surface area and other things, etc. So, right. Next, let us look at if we have a function of two variables and its value is real, we call that as a real valued function of two variables, and in case it is a function of three variables, real valued function of three variables. So, we will look at how to do various calculus concepts for this kind of functions, right. So, first we have already seen how to plot graph of such functions in Sage Math. So, if you want to plot that surface z is equal to fxy, you can use plot 3D. If you want to plot implicitly defined function in three variables, you can use implicit plot 3D. If you want to plot contours, contour underscore plot, and in case the surface is defined using parametric coordinates, you can use parametric plot 3D. So, we have already done, but I request all of you to explore these functions and take some examples, right. Now, when you have a function z is equal to fxy, you can define the limit of this function at x equal to ab, and suppose that limit is a real number alpha, let us say L, then when do we say this limit of fxy at ab exists and it is equal to L? If this says that the limit is equal to L if you take any epsilon positive, then you can find a delta positive such that all take any xy in the disk of radius delta within this domain, and look at the difference between fxy and L in mod, this should be less than epsilon. Okay. So, for every xy inside this U with this condition that x square plus y square in square root, which is the length of the vector xy, this should be less than delta, then the difference between fxy and L should be less than epsilon. And in case the limit exists, we denote that limit as limit f of xy going to ab as L, right. So, in case you are looking at function in R2, in case of one variable you had notion of left hand limit and right hand limit, but in case of two variables you do not have left hand direction, right hand direction, rather you can talk about limit along any curve. So, if you any curve inside U. So, in case you have a curve gamma, which is gamma t is equal to xt yt, where xt and yt are x coordinate and y coordinate of this curve, then and this curve, suppose gamma t goes to AB as t goes to t naught, then limit of f of gamma t as t goes to t naught, if that exists, we say that this limit of this function along this curve gamma exists at t naught, that is at the point a comma b, right. So, and you can show that in case the limit exists of the function, then limit along any curve will exist. But in case the limit does not exist, what does it mean? That means that you can find some curve gamma t in U such that gamma t goes to AB at as t goes to t naught, but the limit of f of gamma t, that is limit of f along the curve, does not exist. Or you can find two curves gamma 1 and gamma 2 both converging to AB, and such that limit of gamma t, gamma 1 limit of f along gamma 1 and limit of f along gamma 2, if they exist and but they are different, then also the limit of the function does not exist. Here f is missing, so I will make this f of x y. Right. So, that is the so this is should be in outside this. Right. So, that these are the thing. If you want to define the limit, you can also define limit along a path. Okay. So, let us take an example. Suppose f x y is equal to 2x square plus y square upon x square minus 2y square. Now, if you look at this function, so let me just show you what is this function f of x comma y, that is the function. And suppose we look at, suppose we put y equal to 0, that means and limit of f of t comma 0 at t goes to 0. So, that means we are taking the y equal to 0 in this is nothing but the x axis. So, we are saying we are finding the limit of this function along x axis at 0 0, this is equal to 2, whereas if I want to find out limit of this about x equal to 0, that is along y axis, this limit is minus half. So, this for this function the limit along x axis is 2, limit along y axis is minus half, therefore, this function does not have limit at 0 0. Any other place it will have limit other than the origin, right. So, if you look at, let us say curve y is equal to mt, as t goes to 0, this mt will go to 0. So, then if you look at y is equal to mt, this curve, that is the line along y equal to mx, the limit of f along the line y equal to mx, this limit this depends upon m. So, if you take various values of m, you will get different limit. So, that is another way of saying that the limit of this function at origin does not exist. If you take for example limit along y equal to t square, this limit is 2, whereas if you take the limit along y equal to 2t, this limit is minus 6 by 7. So, again you can see that along various curves this limit of the function are different and hence the limit does not exist. Similarly, you can take another example. Let us say f of x is equal to 3x plus y square plus 4x y. In this case, if you want to find limit of f x at along, so first we can find the limit at x equal to 1 and for any value y. So, that is a function of y, and again we can find limit of this at y equal to 1. So, that is in particular we are finding the limit first with respect to x and then with respect to y. You could do first with respect to y and then with respect to x, and then see we will get both the same thing. For example, here this is the same thing. If I want to first find with respect to x and then with respect to y, is same as first find with respect to y and then with respect to x. So, right. So, this is what is called iterated limit, right. So, how does one define? We just now saw that in case we find limit along x at any y, that is a function of y. So, we can denote that by gy. Similarly, the limit when we find along y, when y goes to b at any x, that will be function of x. So, that is a small typo, that is a function of x, and then we can define and then suppose the limit of f of x at x equal to ax equal to b, that is x y going to a b, if that exists and is equal to L, then you can show that the limit of gy as y goes to b will be L, and also limit of hx as x goes to a will be L. But this limit of gy as y goes to b is nothing but limit of f of x y as x goes to a, and followed by limit of that with as y goes to b. So, that is these two are what is called we call as iterated limit, and in case the limit exists, it doesn't matter, you can find this limit in any order, right? That's what. So for example, if you look at this function, the function which we looked at earlier, f of x y is equal to 2x square plus y square upon x square minus 2y square. In this case, if you try to find the iterated limit at x equal to 0, y equal to 0, that is the origin. So when we take limit first with respect to x and then with respect to y, in this case this limit is half, minus half, whereas if I take first with respect to y and then with respect to x, this limit is 2. So again, you can see here these two iterated limits are not the same. So that again proves that the limit of this function at 0, 0 doesn't exist, because if the limit exists, then both these iterated limit should have been the same. Since these iterated two limits are not the same, the limit cannot exist, right? So that's a. Next, let us look at if you have a function z is equal to f x y, how do we define continuity of this function at any point a b? So for that, suppose f is a function defined on let us say u, which is subset of R2 to R, and then you need this point at which you want to talk about the continuity inside the domain, and functions should be defined at that in that domain. Then we say that the f is continuous at a b if the limit of f x y at a b exists and the limit is equal to value of the function. That's the standard definition. Of course, one can also define limit and continuity using sequential approach. So you can talk about sequence in R2 and in general in R3, in Rn, etc., and its convergence. So we say that function f at fxy at ab is continuous if you take any sequence x and y n converging to ab, then f of x and y n should converge to f of ab. Okay, so that can also be taken as a definition and solve all the problems using that. So let us take an example. So suppose you have f x y is equal to, let us say, 5x y square upon x square plus y square. Now if you look at this graph of this function, suppose we plot graph of this function, then this graph looks like this. So at the origin, you can see here there is hardly any, there is no break actually, though the function has some strange behavior at the origin, but this function has to be continuous at 0, 0, right. So let us look at, suppose we want to find the iterated limit. This limit is 0, similar to the other one, this is 0. So first, it doesn't matter whether you find limit with respect to x equal to 0 first and then y equal to 0, or you first find with respect to y equal to 0, y at 0 and then find x equal to 0, both are the same. So it also, of course, when you want to prove the existence of the limit, the best thing is to use epsilon delta definition. So this and epsilon delta definition, working with epsilon delta definition or given any epsilon finding delta using any software may not be all that convenient. So here what we are trying to do is we are just trying to find out the limit and then say whether they're equal, right. So in this case, you can see here this these two limits are the same, and limit is 0, which is the value of the function at the origin. Therefore this function is a continuous function, right. So you can look at other functions, and all these definitions in 2 variables can be extended to 3 variables and n variables, right. So let me leave you with some simple exercises that you can try. So these are the few exercises. First, find the area bounded by one loop of this polar curve. Similarly, find the arc length of this particular curve between 0 to 2 pi. Find the area that curve this encloses, and find the area of the surface generated by rotating a polar curve. R is equal to f theta. Theta varies between a and b, and you need to assume that a is strictly less than b and both lies between 0 and pi. And in that case, this area is given by integral of 2 pi r sin theta square root of r square plus dr by d theta whole square d theta, and this limits are between a and b. So this again, this you can obtain this formula of area of surface from the Cartesian coordinate. You already know Cartesian coordinate formula, so you just use change of variable, you will get the answer. And next two problems are on limits. So try to find this, show that the limit of this function exists, but limit of this function does not exist. So let me write here, this is bracket is missing. No, sorry, this y2 should be y square, and this bracket extra I will remove. So these two are very simple exercises, right? Okay, so thank you very much. I'll see you in the next class, and in the next class we will look at partial derivatives and various concepts related to partial derivatives.